Welcome to today's paper reading. Today's paper is titled, Mutual Reasoning Makes Smaller LLMs Stronger Problem Solvers. This paper was published on the AR14 preprint by Zhenting and colleagues from Microsoft Research Asia and Harvard University. This paper introduces rStar, a novel self-play mutual reasoning approach designed to significantly enhance the reasoning capabilities of small language models, SLMs, without the need for fine-tuning or access to superior models. rStar decouples the reasoning process into a generation-discrimination mechanism. Initially, a target SLM augments the Monte Carlo Tree Search, MCTS, with a variety of human-like reasoning actions to construct higher-quality reasoning trajectories. Subsequently, another SLM, with capabilities comparable to the target SLM, acts as a discriminator to verify each trajectory generated by the target SLM. Reasoning trajectories that are mutually agreed upon are considered mutually consistent and are more likely to be correct. Extensive experiments conducted across 5 SLMs demonstrate that rStar can effectively solve a diverse array of reasoning problems, including GSM-8K, GSM-Hard, Math, SVAMP, and Strategy QA. Notably, rStar achieves significant accuracy improvements, such as boosting GSM-8K accuracy from 12.51% to 63.91% for Llama 2-7B, from 36.46% to 81.88% for Mistral 7B, and from 74.53% to 91.13% for Llama 3-8B Instruct. The code for this approach will be made available. Large language models, LLMs, face significant challenges in complex reasoning tasks. For instance, models like Mistral 7B achieve only 36.5% accuracy on the GSM-8K dataset, even with advanced techniques such as chain of thought, COT. Fine-tuning has been shown to improve reasoning capabilities, but often relies on data distilled by superior models like GPT-4. The community has been exploring ways to enhance reasoning without such superior models. A promising approach is leveraging the knowledge within LLMs themselves, but this often suffers from issues like ineffective exploration of the solution space and difficulty in determining reasoning step quality. This paper introduces rStar, a novel approach that enhances reasoning capabilities through a self-play mutual generation discrimination process, addressing these challenges by employing mutual consistency feedback. Figure 1 illustrates how rStar, through 32 rounds of inference, significantly enhances the reasoning capabilities of small language models, SLMs. This enhancement makes these models highly capable problem solvers, achieving reasoning performance that matches or even surpasses that achieved after domain-specialized supervised fine-tuning, SFT. The figure highlights the transformative impact of rStar on SLMs, demonstrating their potential to perform at levels previously only attainable through more complex and resource-intensive methods. Figure 2 illustrates the self-play mutual reasoning process, which is a generation discrimination mechanism. Initially, a self-generator enhances the target SLM to produce candidate reasoning trajectories using Monte Carlo Tree Search, MCTS. Subsequently, a discriminator, employing another SLM, offers unsupervised feedback on each trajectory, guided by partial hints. Finally, the target SLM evaluates this feedback to determine the optimal reasoning trajectory as the solution. In the related work section, the authors discuss several key areas of research. Firstly, prompting language models to enhance reasoning performance, which includes methods like chain of thought, planning, and problem decomposition. Secondly, the self-improvement of large language models through fine-tuning and advanced prompting techniques such as self-verification and RAP. Lastly, the sampling of reasoning paths to improve performance, which involves techniques like self-consistency and tree search, though these often have limited action spaces. The methodology section introduces a novel approach to solving reasoning problems using large language models, SLMs. The problem is formulated as a multi-step reasoning generation task, which is more effective than traditional chain of thought, COT methods. This approach leverages the Monte Carlo Tree Search, MCTS, algorithm to augment the SLM, allowing it to incrementally build a search tree. However, challenges arise due to the vast solution space and difficulties in accurately rewarding each action. To address these, the rStar methodology is proposed, which includes a richer set of human-like reasoning actions, a tailored reward function for SLMs, and a mutual verification process using another SLM as a discriminator. Figure 3 illustrates the process of self-generator within the context of Monte Carlo Tree Search, MCTS. The figure highlights nodes from top to bottom, which together form a complete reasoning trace. Given a question, MCTS enhances the target SLM by exploring a diverse, human-like reasoning action space. This exploration allows the SLM to generate subsequent reasoning steps based on the current state, facilitating a more robust and human-like reasoning process. Figure 4 illustrates the process of mutual reasoning consistency, where another SLM, referred to as the discriminator SLM2, is used to verify the reasoning steps of candidate trajectories. This involves masking part of the reasoning steps and prompting the discriminator to complete the remaining steps based on the initial reasoning provided. If the completed steps match the original trajectory, the trajectory is considered validated. This method ensures that the final selected trajectory is more likely to contain the correct answer, enhancing the reliability of the reasoning process. Table 1 presents an ablation study on the effectiveness of a rich action space, evaluating Llama 3-8B on 200 sampled GSM-8K questions. The study shows that the inclusion of various actions significantly improves reasoning accuracy. For instance, the base action space A3, RAP, yields an accuracy of 70.5, while the combination of all actions, A1 plus A2 plus A3 plus A4 plus A5, achieves the highest accuracy of 75.0. This table highlights the critical role each action plays in enhancing the final reasoning accuracy. In this section, we discuss the experimental evaluation of rStar. The evaluation involves 5 state-of-the-art language models, SLMs, and spans across 5 reasoning tasks, including 4 mathematical tasks and 1 common-sense reasoning task. The implementation details include the use of Monte Carlo Tree Search, MCTS, with 32 rollouts, varying depth settings for different tasks, and the use of Phi3 Mini 4K as the discriminator for trajectory verification. The main results show that rStar significantly improves reasoning accuracy across various SLMs and tasks, demonstrating its effectiveness in enhancing the problem-solving capabilities of SLMs. Table 2 illustrates the significant improvement in reasoning accuracy achieved by rStar across various SLMs and reasoning tasks. Notably, Llama 2-7B's accuracy on GSM-8K increased from 12.51% to 63.91% with rStar, nearly matching fine-tuned models. Similarly, Mistral 7B with rStar outperforms fine-tuned MetaMath by 4.18%. The table also highlights that rStar, generator at MOSH, consistently achieves higher accuracy than RAP, TOT, and SC, demonstrating the effectiveness of the MCTS generator even without the discriminator. Figure 5 illustrates the performance comparison of rStar, SC, and RAP on the GSM-8K dataset under varying rollout numbers. Notably, rStar demonstrates significant improvement in reasoning accuracy even with only 2 rollouts. Both rStar and SC show benefits from increased rollouts, whereas RAP's performance tends to plateau and even decline after 4 rollouts, likely due to the limitations of its single-type action space and effective MCTS exploration. Table 3 presents a comparison of reasoning performance on the Math 500 dataset, focusing on the Llama 3-8B Instruct and Phi3 Mini 4K Instruct models. The dataset's extensive latex syntax poses a significant challenge for pre-trained large language models, LLMs, in instruction following. The results indicate varying levels of accuracy across different methods, with Llama 3-8B Instruct ranging from 5.80% to 42.94%, and Phi3 Mini 4K ranging from 3.60% to 48.60%. This highlights the difficulty in handling complex mathematical expressions and the need for specialized models to effectively process such content. Table 4 presents an ablation study on the effectiveness of our MCTS generator. The study compares our generator with 3 baselines, RAP's MCTS generator, SC with 128 randomly sampled solutions, and our generator with self-evaluation. The results show that our generator consistently outperforms the baselines across different answer verification methods, highlighting the effectiveness of our approach. Notably, the inclusion of self-evaluation, which prompts the model to self-reward each intermediate action, reduces the generator's accuracy, indicating the importance of our tailored reward function. Table 5 presents an ablation study on the effectiveness of discriminators in verifying solution trajectories on the GSM-8K dataset. The left section shows that our discriminator consistently outperforms the majority voting, MASH, and self-verification baselines. The right section examines the impact of different discriminator models, revealing that while the choice of model affects accuracy, even the powerful GPT-4 only slightly improves performance over standard SLMs, indicating the robustness of our mutual reasoning consistency approach. In this study, the authors introduce rStar, a novel generator discriminator self-play method designed to significantly enhance the reasoning capabilities of large language models, SLMs, during inference. This approach demonstrates that SLMs like Llama 2-7b already possess robust reasoning skills before undergoing domain-specific supervised fine-tuning. rStar has achieved state-of-the-art results across 5 SLMs and 5 distinct reasoning tasks, significantly surpassing existing multi-round prompting and self-improvement techniques. Additionally, the authors conducted extensive ablation studies and analyses, contributing valuable insights towards the development of more advanced SLM self-improvement reasoning strategies. Thank you for watching.